Most approaches to collaborative transport assume robots can grasp the object with purpose-built end effectors. Yet many real-world payloads, furniture, boxes, or barrels, provide no such grasp points. In these cases, robots must move the object purely by applying pressure to its surface. Moving objects with robots is a rich area of research, with each system relying on its own assumptions. Our focus is on tandem transport with non-prehensile end effectors in hardware, using only 2 mobile robots, a gap not addressed in the existing literature. We begin with an optimal trajectory planner. Given a start and goal position for the payload, motion is cast as a constrained optimization problem, minimizing snap, angular momentum, and its rate of change, rewards alignment between the payload's yaw and the tangent of its path. Finally, it enforces tracking and boundary conditions, ensuring the payload follows a smooth path to the goal. The planner exploits a quadratic program, guaranteeing a unique global solution that can be solved efficiently in linear time. The resulting path minimizes angular torque, sudden changes in acceleration, while achieving the goal position. However, once we move from simulation to hardware, the reality gap becomes unavoidable. The planner cannot fully capture surface friction, contact variability, or unmodeled dynamics, such as small slips at the robot payload interface. To address this gap, we add an admittance controller. In simple terms, admittance acts like a virtual spring damper system. When the robots feel a force from the payload, they don't resist rigidly, but instead move slightly in response, as though connected by springs and dampers. Unlike real springs, these virtual parameters are defined in software. That means we can tune stiffness, damping, and the inertia to achieve the right balance between compliance and stability. A pre-tuned admittance controller does perform better than no admittance at all. In our tests, it completed the task in 5 out of 20 trials, but the limitations are clear. In all but one of those successful cases, the payload slipped during transport, showing that it was not held securely. Our main contribution is dynamic admittance parameterization. Instead of relying on fixed gains, we adapt stiffness, damping, and inertia online, based on real-time estimates of the reality gap and our confidence in those estimates. The controller continuously adjusts the end effector targets and modulates compliance to suppress oscillations while maintaining stable contact. In hardware, this adaptive scheme substantially reduces slip and misalignment. Whereas static admittance often loses contact with the payload, dynamic admittance maintains stable coupling between robots and payload.